In Proposition 14, we're going to prove the converse of Proposition 13. Here we're going to show that if we have lines such that the adjacent angles make two right angles, then the two straight lines on opposite sides making those adjacent angles must be in a straight line with one another. Let's check out the text. If with any straight line, and at a point on it, two straight lines not lying on the same side make the adjacent angles equal to two right angles, the two straight lines will be in the straight line with one another. So in terms of the diagram, what he's saying is that if we start with some point, let's say this is our point of interest, and let's say we've got some line over here, and another line down here. He's saying that if these adjacent angles make two right angles, then this segment must be in a straight line with that segment. That's the claim. Now we're going to go through the proof. For with any straight line AB, and at the point B on it, so we have the point B right here. We'll say this is B. This is going to be A. Let the two straight lines BC and BD not lying on the same side. So I'll place that in here. Here's B to C. And B to D over here. And they make the adjacent angles ABC, so ABC right there, and ABD. Now he's saying that if those two angles are equal to two right angles, then it follows that BD is in a straight line with CB. And the way we're going to prove this is a proof by contradiction. We're going to assume the negation. And for the sake of argument, we're going to assume the situation is more like this. Let's say BD is not in the straight line with CB. So the situation is more like this. So we're going to suppose that BD isn't in a straight line with BC, and yet CBA and ABD still sum up to two right angles. We're going to draw out the absurdity of this situation. Next, he says, for if BD is not in the straight line with BC, that's our supposition, which we attempt to show that this implies an absurdity, let BE be in a straight line with CB. So all we're going to do is extend CB in a straight line, and we'll call this point over here E. So that's what he means. Let BE be in a straight line with CB. Then, since the straight line AB stands on the straight line CBE, the angles ABC and ABE are equal to two right angles. Now, why is that true? That was proved in the previous proposition. But the angles ABC, where's ABC? That's right here, and ABD are also equal to two right angles. Remember, that was the given, that these two guys are equal to two right angles. And what follows from that, therefore, the angles CBA, so CBA, and ABE are equal to the angles CBA and ABD. Why does that follow? Things which are equal to the same are equal to each other. And the fourth postulate, which says that all right angles are equal to one another, and that's needed to make that inference using common notion 1. And let's now draw out the absurdity. Let the angle CBA be subtracted from each. So from those, we're going to just take away CBA. Now, therefore, the remaining angle ABE, this is the remaining angle ABE, is equal to the remaining angle ABD. Why are these two angles equal? Well, from common notion 3, equals subtracted from equals generate equals. And you can see from this diagram, we're going to have a problem. the less to the greater, which is impossible. So what is he saying? Notice ABE is equal to ABD, but ABD is a part of ABE, and if it's a part of it, it can't be equal to it. Therefore, this BE that we drew in here is not in the straight line with CB. And he continues, similarly, we can prove that neither is any other straight line except BD. Therefore, CB is in a straight line with BD.